I'm going to go ahead and do examples 3, 4, and 5 from the end of the note pack of the extra practice where it's energy blended with other units. I did 1 and 2 in class, so I'm not going to do those here. I know one of the hours I did 3 in class and the other one I did 4. So I'm just going to do 3, 4, and then I know I didn't do 5 with anybody. So here we go. Our first one in the diagram above, you have a block, has a mass of 250 grams. So I'm going to convert that immediately to kilograms. Push against a spring has a spring constant of, so my spring constant, 750 newtons per meter. We have a horizontal friction on the surface. However, the ramp has a coefficient of friction. Coefficient of friction is 0.45 for the ramp. And when it's released, it reaches a height of 0.65. So this is a little tricky about the ramp. So it's going to make it 0.65 meters of vertical height, 20 degrees. Using SOHCAHTOA, I can figure out this distance x, which I will need for friction. So using SOHCAHTOA, it's going to be 0.65 divided by the sine of 20 degrees. I got 1.90 meters. So that includes my ramp, and then I think we're good to go. So it says first things first, determine the force of friction that the ramp will apply to the block. So using forces in a free body diagram, we have mg, Fn, and since my block goes up the ramp, friction's down. And the direction of motion, I will have a negative force of friction equals ma. I'm not actually going to need that. You'll see why in a moment. It's actually not even complete. I also have gravity's component down the ramp, so for the sake of completion, minus mg sine theta equals ma. Perpendicular, I will have normal minus mg cosine theta equals 0. Whole point of that declares the normal force is mg cosine theta. The reason why I care about that is because my force of friction, by definition, is mu Fn. So that's mu mg cosine theta. That'd be a 0.45, 0.250. I'm going to use 10 for g because why not? Cosine 20 and resort to a calculator. Tells me the force of friction is 1.06 newtons. So that checks off A. Determine the work done on friction by friction on the block as it moves up the ramp. So this is A. All right, B. Work from friction is Fx cosine theta. Now, this is where we get into the weird situation. The force of friction is down the ramp and x is up the ramp this way. So it's 180 degrees, and the cosine of 180 degrees will be a negative 1. So the work done by friction is negative. That's effectively what it's telling me. I'm going to not really worry about that negative because I'm going to handle it when we get into C and D, what's going on with the spring and with kinetic energy. If you want to put the negative 1 in there, go ahead. It's not going to hurt anything. 1.06 by 1.9. Whether you do negative or positive isn't that big of a deal. Ultimately, what I can declare is that friction took away 2.01 joules of energy. And part C says determine the velocity of the block just before it reaches the ramp. So for part C, I'm going to hit on the fact that kinetic energy at the bottom of the ramp turns into gravitational potential energy at the top of the ramp, except along the way 2.01 joules is taken away by friction. So this is where that whole positive and negative thing comes into play. Depends on how you want to write this. You could say kinetic minus 2.01. So the kinetic energy minus the 2.01 friction takes away. Whatever's left over becomes potential. Or the kinetic energy manifests itself as 2.01 joules lost to friction and the potential. It really doesn't matter. I mean, both of these equations are the same thing. So I'm just going to go with the one up top. The goal was to find the velocity of the block. So we're looking at 1/2 mv squared for kinetic minus a 2.01 mgh 0.250 because it was 250 grams. And once again, 0.250, 10, the height 0.65 that was given in the problem earlier. You will have a nice algebra problem for you to solve, and if done correctly, if I'm doing it correctly, it should go out to 5.39 meters per second. I'm just going to do a double check on that and make sure before I, submit this for the whole world to see. Yep, checks out again. Okay. So that answers part C. Determine the velocity of the block just before it reaches the ramp. And the last one, how much energy is the spring, or how much the spring was compressed before releasing the block. So D takes us back even a step further. That spring potential energy became the kinetic energy that we just discussed on the block. So the 1/2 kx squared, there's no loss to friction or any other force in this transfer from spring to kinetic. It gave me a spring constant of 750. So I'll go 750 x squared equals 0.250, 5.39 squared. And almost, I got x equals 0.98, whoops, 0.0984 meters. I'll run one more check just to be safe. And it looks like we're good. So that takes care of example 3. Let's move to example 4. This is energy and projectile motion. So energy, projectile motion. It wants to know what is D, what is H, and I think that's it. Yep. It's a frictionless surface and a frictionless ramp inclined at 30 degrees. So we're going to focus on the start situation here and the situation in which we leave the ramp. The ramp is 1.5 meters tall. So I'm now going to declare the energy at A will be equal to the energy at B. At position A, I have spring energy only. At B, I have potential because I've gained 1.5 meters. I have kinetic because I'm moving. So 1/2 kx for position A squared equals mgh for position B plus 1/2 mv for position B squared. A 1/2 550 expresses the spring constant by a total of 0.30, 30 centimeters, so we got to convert that. Mass is 200 grams, so that's 0.2. G is 10, height is 1.50, 1/2 0.200 VB squared. Alright, so I am doing all of this purposefully so I can figure out how fast I leave the ramp. If I figure out how fast I leave the ramp, that will allow me to turn this into a projectile motion question, going back to Unit 1. All right, so I got 14.7 meters per second for VB. From here, we're officially leaving the wonderful world of energy and going into the wonderful world of kinematics. This is a 30-degree angle. We'll use SOHCAHTOA 14.7 by cosine 30. So the x is 12.7. And 14.7 by sine 30. So it's a half. 7.35. Let's break things up into an XY table. I would like to know delta x. I don't. V initial for the x is 12.7. And that's all I know. Y direction. V initial for the y is 7.35. Acceleration for the y is negative, I'm going to do negative 10 meters per second squared. Delta y is a negative 1.50 meters. Okay. You got two options here. What you have to do is find time. My tip whenever you're not sure where to go on this, when in doubt, find time. By the way, if you hear any chewing in the background, sorry, my dog just came in with a bone. So when in doubt, find time. So I'm going to use this y information to find the time. I can use the second equation. If I do that, I will need the quadratic formula. The other way to bypass that is to do v squared is v naught squared plus 2a delta y. Then, once you know what v final is, you can do v is v initial plus at and solve the time. I don't care which way you go. I'm going to do this way because I'm just going to have the calculator run the quadratic formula for me because I can. And I mean, there's nothing wrong with you doing that either. It's not a math class. We're not asking you to show us the work for the quadratic formula. So I do have it set up here. I'm going to, let's see, I'm going to plug in my values 735, and this one was 1.5. Calculate. It did not go backwards in time, so we're going to go with 1.65 seconds. So t 1.65 seconds. I can put t here, 1.65 seconds. Delta x is v naught xt. So delta x, also known as b, 12.7 by 1.65. Uh, 21.0. So I've checked off, I found d, determined the height as well as total distance, so I've done that one. Height is its own standalone thing in the wonderful world of projectile. So the height, v final for the height is 0 because you've reached a peak. Acceleration still negative 10, and the v initial is still the 7.35 I found earlier. I'm going to use v squared as v naught squared plus 2a delta y. There will be one more trick that you got to pay attention to at the end of this, but otherwise it's mostly plug and chug. You will solve, in my particular case, dividing out 20. Delta y is 2.70. Now you have to be careful because what you've solved is this. 2.70. You have solved the gain in height from this position in which you're moving at 7.35. So with that in mind, you have to make sure you add the 1.5. And then you'll get let's come to 4.20 meters. And determine the height. Done.